Hey class, today we're going to finish up our lessons on discrete probability and move on to advanced counting techniques. But before we do that, I wanted to review a problem that I ran across several years ago, and it just kind of shows some of the ways that you can use random variables to produce interesting results. And so if you have a random variable that is distributed, is uniformly distributed through the values 0 and 1, then you can take a square running from 0, 0 to 1, 0 to 1, 1 to 0, 1, just that first square in the first quadrant of the Cartesian plane, and you can imagine extending it into the other quadrants. And using it to contain the unit circle. So just the circle centered at the origin with radius 1. Okay. But coming back to random variables, so if you were to draw the variables in pairs, if you were to request the next random variable and get some value x, and then use the next one for y, and so you're always drawing them in pairs, then you would end up getting a plot all between 0 and 1 for the x and 0 and 1 for the y value. And it would end up with a fair distribution. It would end up with following those principles of uniform distribution. And so you would get this kind of splattering all across this first square. Some lying within this quarter of the unit circle, and some lying without. And so the interesting result of this is this tendency towards some limit. So whenever you draw a single random variable, it's extremely biased. It doesn't appear to be uniformly distributed at all. It's located in exactly one spot. But the more variables you draw, the more variables you consume, I should say, the more random variables you consume, the more it begins to take a shape that appears to be fairly distributed. It appears to be uniformly distributed. It's the same thing with the roll of the die. If you roll 2 6s in a row, it seems like the die is rigged. But if you roll the die 360 times and you find out that 2 of the 6 sides came up exactly 60 times, 2 of them came up 61 times, and the other 2 came up 59 times, and that die turns out to be extremely fair. So the more samples that you get, the larger your sample set, the greater the tendency towards this uniformness of distribution. And so if you use the computers or the random number generator from any program on your computer, and you simulate this where you draw an x and you draw a y, then and you measure whether or not the dot fell interior to this arc, this circular arc, or exterior, using this function. So if x squared plus y squared is less than or equal to 1, so a squared plus b squared equals c squared, will give you the arc, the unit length arc that it creates the circle, and then anything less than or equal to that, the r squared here, would tell you that it's inside the circle, and anything greater than that would tell you that it's outside. So then if you measured the ratio of those that fell inside, so interior, to all of them, right? then you would get the ratio of the area inside the circle to the overall area, right? So this is a 1 by 1 square, so the denominator is 1, and then this is 1/4 the area of the unit circle, so this would be pi over 4, right? Because the area of the unit circle is pi r squared, where because it's unit length, r is 1, so it's pi times 1 squared, so pi. So then 1/4 of that is pi over 4. So then this experiment it would converge this ratio towards pi over 4. And so you can use this value and random variables and this project, or this method, to statistically compute an approximation to the value of pi. And so I just thought that was a really cool way to use statistics and random variables and to understand how distributions tend, if you have something that's uniformly distributed, that you could use its tendency to even out kind of in a fair way to approximate something that is irrational. Okay, that was the pre-lesson lesson for the day. Let's jump back into our discrete probability. We'll pick up with Bayes' theorem, and we'll try to make our way as far into Chapter 8 as we can. And then remember to check online for the homework today. It will be posted sometime before midnight. Okay, so we ended last time on the concept of a random variable. And it is just essentially a variable that falls in some range, and it is hopefully not terribly predictable. If it is, then it's not all that random. Okay, so one thing that I do want to complain about, I do want to spend a little bit of time whining, and hopefully seeing your instructor or hearing your instructor do that will show you that it's also fair to do that as well, is that I'm not a terribly big fan of the way that they assign variables, or the way, just the notation around these next couple of sections. Just because it's very different from the rest of the book, or I guess my favorite subjects like real analysis and algebra, but complex analysis is really fun too, and anyway, math in general is really fun. Let me take that back. But so just try not. My point in all of this complaining and whining and so forth is to encourage you to just kind of push through the discomfort you may feel as you read, and the notation feels a little foreign. It's okay. You're gonna make it through. So and you're not alone in finding it just a little bit different than what's familiar. But once it does become familiar, you will hopefully not have too much trouble with it. So so Bayes' theorem, it essentially relates the probability of some event f given E to the probability of E given F. And so you can look at it in a couple of ways. So first, you can see this normalization. So we have the probability, we're dividing by the probability of E, and that's kind of this normalizing act. Well, if we're given that E happened, and we're measuring a probability given that E did happen, then we want to scale for that. We want to correct for whatever probability it is that we're testing for, in this case F, by that value that we already know happened. So we want to take that out of the fold, which is why we're dividing it here. But at the same time, that's not exactly, and it's not strictly how this formula was derived. So if you look in the book, you can see that it relates these probabilities using the probability of E intersect F, so the probability that both events happen. And then it's able to correct for that and make some substitutions and eventually derive this formula. But there's, like I said, there's multiple ways to interpret what is actually happening here. But the key feature of this theorem is that it relates the conditional probability of F given E to the probability of E given F. And so you can certainly see other symmetry if you move this term over here, and you see that it's probability of F given E times the probability of E, and the probability of E given F times the probability of F. And then we'd already discussed the gambler's delight, right? The parlay, where you have to win every part of your bet in order to win the grand prize that you're gambling for. And so that's kind of what's happening here, right? So in that case, it's the probability of F times the probability of E, and this doesn't really matter, that you're conditioning it on E because you have to win both, and so it's essentially the probability of F times the probability of E, right? But and then you can see that over here. So it's essentially saying, well, we only care about this if we win this first bet, and so forth. But like I said, there's many ways to interpret this. And then the theorem itself, as presented in the book, goes even a step further. And then it creates that relationship. It extends this definition, or this interpretation, to this by stating that the probability of E is equal to the probability of E given F times the probability of F plus the probability of E given not F times the probability of not F, right? And so essentially, it's saying, well, the probability of E can be broken up into the probability of E, since we're measuring two events, the probability of E when F happens, and the probability of E when anything but F happens, right? So that's all we're doing here, and this interpretation is a little less memorable than this in my estimation, but whatever. Okay, and so this version of Bayes' theorem will feed into the generalized version of Bayes' theorem, where you're measuring the probability of some event J, F sub J given E, and then you get this formula where it's equal to the probability of E given F sub J times the probability of F sub J. So exactly the same as this. But the probability of E is now broken up into all of these components, right? So the probability of E given that the first thing happened, or the second thing happened, or the third thing happened, right? And so this is the generalized form. Okay, so why is this theorem interesting? Does it matter beyond whatever stat test or problem on some exam that this problem may appear? And the answer is yeah. So it's this particular theorem is interesting because it allows us to update probabilities, right? So I sometimes follow sporting events on ESPN or whatever, and if you can't watch the game, they will stream these the scoreboard, and they'll show you every additional play, and then it'll give you some stat like what is the probability that this team will win given the current situation, right? So the current down and distance in the current quarter with the score as it is, and so forth. And so with each play, that probability gets updated. So if you get sacked for a 30-yard loss or something, then it updates, the probability of some event happening. And so if you're so beyond sports, right, and gambling, which gambling is real important to the history of statistics, right? So beyond that, if you want to measure something that kind of bounces around a lot, and all you can really do is measure it with some likelihood, such as the stock market, then the Bayesian statistics, so this ability to update the likelihood of a given event given some other event or series of events, will be determined by, at least at some fundamental level, by these formulae. So, this form is not so difficult to remember. This one, if you remember that this is just, you're measuring the probability of E given that F happened or it didn't happen, and you kind of remember that or operations become pluses and so forth, right? Then this one's not so hard to get to from here. And even this one is not too terrible if you just realize that this is, instead of A or not A, it's A or B or C all the way up to N, right? Then you could get here as well in not too terrible of an effort, right? But yeah, so these theorems, and they seem very, very ethereal, very hard to really even reckon with. They do have some meaning and some provide some insight into very complex systems, and so I wanted to make sure that we took a moment to go over this and emphasize that it may take a little while, or you may have to overlap in some other discipline for it to come up, but these theorems do come up again under certain scenarios. And the importance is, and the thing I want you to keep in the back of your mind, is that there is a theorem, and this is it, that allows you to update the likelihood of an event based on some other thing that has happened. Okay, so expected value and variance. So going back to the dartboard, or the expected value would be a bullseye, essentially, right? So if you have some scattering of darts, and you take their average, which is really all that an expected value or a mean is, then the likelihood is that they will average a bullseye. But as we all know, bullseyes themselves are incredibly rare, and so what we're really seeing, like the value that tells the true story of how bad we all are at darts, is more so the deviation or the variance for these dart throws. Okay, and I believe we come down to those later. Yeah, variance and standard deviation are given a little bit later. So I just want to state again that the expected value is really just an average of the overall distribution, and so, but it really just gives kind of a starting point. It gives the origin for the rest of the story told by the statistics. It is not what we actually necessarily expect to happen, right? Or if you just discuss pregnancies, and expected due dates. So only 5% of babies are delivered on their due date. The rest all happen, more or less, plus or minus a week, and then in some extreme cases, up to 2 weeks later, and premature babies can come much sooner. But if your expected value is only happening 5% of the time, it seems like a bit of a misnomer. And so I just want to get across that it's not necessarily what we expect to happen. It's just like this average of the overall distribution. Okay. Okay, and so here's another example, okay, so yeah, this is kind of perfect for that. So what is the expected value of a fair die roll? The values can achieve 1 through 6, and we have a formula for this, right? So we're given this summation, and we're computing expected value of x. Okay? Essentially, all you do is average it. So each one gets 1/6 of a say in what's coming out, right? Because the probability of a fair die is that each event would happen 1/6 of the time. And so the first value is 1, and we're fortunate to have simple numerical values to discuss in this, right? So the first one is a 1, and then 2, and so forth, all the way up to 6, again, each with 1/6 probability. So they all have a common denominator, so we just add them all up, and we get 21, and then we divide it by that common denominator, and then we reduce, and then we get the expected value is the average, essentially, of all of these. That is 7/2, right? So 3.5 is not a real possibility for die, which yields an integer result. But it just shows that that in this case that's what the expected value would be. So just because it's not an actually possible result, it doesn't mean that it's not the correct answer for the expected value, right? So again, it's not telling the full story. There's something else that would describe this a little bit better, and would be that it's a uniform distribution of integer values 1 through 6. Okay. So the next is let's see. Okay, so what is the probability that x is equal to some specific value r for some sample set S? And so it's in this case, it's the sum of the probabilities of everything that yields x equal to r. So if you think dice roll again, and you're rolling 2 die, so what is the likelihood that we roll a 7? And so it's the sum of the probabilities of everything that adds up to 7, right? So it's not so simple as when we're rolling just a single die. Now we're having these contingent values, or these dependencies, where we want the probability of a 1 and a 6, the probability of a 2 and a 5, the probability of a 3 and a 4, and so forth. And so fancy notation, but that's where the sum is. So if x equals r is satisfied by a handful of events, such as in rolling a pair of dice, then you use the summation and you add up those probabilities. So each one of those pairings had a 1 in 6, a 1 in 36 probability of happening, but there's 6 of them that satisfy it. So you have a 1 in 6 chance of getting a 7. So, okay, and then the expected value of x is, again, now you have these weights that you can apply, and you've computed this from here. So then the probability of rolling a 7 times, not just 7, right? But this, again, using the pair of dice, you now have the chance of rolling everything from a 2 to a 12. And so the expected value is this weighted probability of rolling a 2 times the value 2, plus the weighted probability of rolling a 3 times the value 3, and so forth up to until you've done all of the possibilities in the sample set. And then those averages will give you the expected value. and the expected value in that case is a 7. Okay. So the expected number of successes in n mutually independent Bernoulli trials are performed, where P is the probability of success on each trial is n times P. Okay, so what did that tell us? Well, Bernoulli trials are like coin flips, right? So anytime you hear Bernoulli trial or anything like that, you can just substitute that. So if we flip, and then for these values, just to make a sense of it, I always replace actual numbers just so I can get a feel for what it's trying to say, right? So if we Bernoulli trial, right? So if we flip a coin n times, we'll choose 100 times, and the probability of getting success, so we'll say heads is success, right? And the probability of getting heads is 1 out of 2. Then the expected number of successes, which we've set as heads, on 100 coin flips, where it's a 50-50 proposition, right, is 100 times 1/2. So we would expect to get 50 heads on 100 coin flips. Okay. And then the next theorem. Okay, just shows that the expected values can be pulled out, right? So we can separate the expected value for x1 and x2 and xn and it also has the property of linearity, right? So in addition to being able to separate additively like this, we can also pull it out. We can pull out the constant times x, and then b is in fact a constant rather than a random variable. So there's no variance on that, and so I feel like this definitely needs an example. I'll have to go back into the book and see if I can find an example that displays what it is that we're looking at here, because I can't, off the top of my head, come up with a good indication for when this applies and when it doesn't. So my apologies, but we will pick that up on the second pass, hopefully. Okay. So geometric distribution, yada yada yada. So what is the likelihood, or how long do we have to wait until we get this first event to happen? And so a geometric distribution gives a particular answer to that. So the amount of time it takes until we get our first success, right? So for a coin flip, we would expect to get heads or tails after 2 flips, and that's this 1 minus p. So we assume that we fail, right? So if we're measuring for p, then we assume that we fail k minus 1 times, and then on the kth trial we get our success. And so whenever this is the case, whenever it follows this pattern, then we say that it has a geometric distribution. Right, and so 1 over p. Yeah, so I understand the geometric distribution because of this, and what I find is interesting is that it tends towards this harmonic property. But I guess it's only harmonic if it's part of a series, so never mind that. Okay. We give a definition for independent variables. and if the probability, and so this is going in the other direction, right? So we already know that if two variables are independent, then the probability of both of them happening are p of x times p of y, right? Probability of x happening times the probability of y happening is equal to the probability of both happening. And so this defines it in the other direction. So if you have something that meets this criteria, where whenever you measure both, it's equal to the probability of them happening individually, then you can see that they're independent. And the example that I describe here is a case where you can measure, like, again, sample spaces, right? So you take the measurements and then you go back and you try and derive the formula, as opposed to, games of chance and other things where the probability can be counted from some logical origin. In these cases, you're not exactly sure what's at play, and so you take the samples first, and then you go back and you make your measurements, and find out what variables are dependent and which variables are independent. And so the example I give is for dogs, but it works on foxes as well. So if you measure generation after generation, and you chart the tendency of dogs, of breeds of dogs, to have floppy ears and playful tendencies, if these are two separate characteristics that you're measuring, and you measure the likelihood that they would have both, if it's not equal to the independent likelihood of floppy ears times playful disposition, then they're not independent. And so in this case, like, this is an example of where you could take a sample space and you can make your measurements, and you can use the results to show that there's correlation, that they happen together. So you have this mental disposition, which isn't really considered a phenotype, and this physical manifestation, the floppy ears, and you wouldn't expect the physical appearance to actually affect or relate to the animal's tendencies towards children, towards people, or other animals, and yet they do. And so that's an example of correlation rather than independent variables. And so this definition, while it seems like we've kind of already gone over this, it just goes to show that that there is another way of defining it. And so that's also not the only way to show that two variables are independent, and so, or correlated, right? So if you want to show correlation, then typically you would chart the variables together, and you would show that there's a tight variance, a tight distribution about some mean, some linear regression line passing through there, so that you can see that they are very much related to one another, right? But this is just another way of showing independence, or of a way to indicate a failure to be independent as variables. Okay, so x and y are random variables, yeah, again. So if they're independent, then you again get that the expected value, this is actually different. The expected value of x times y is equal to expected value of x times the expected value of y. Right, so it's expected value rather than probability, but it still obeys that that property where evaluation after multiplication is equal to multiplication after evaluation separately. Okay. So variance and standard deviation, these are very similar concepts. So they both, again, tell how spread out your results are, how wild the results are. So wild in the sense of dart throwing, so how wild the player is in their throws. And so variance is a little more what we would expect if we define it. So we see this squared term in here, And that's just to make sure that any error, whether it's above or below what we were expecting, right? And if the terminology, if the symbols are confusing you, you can just replace e of x, so the expected value of x anywhere, with the average. So with the average over the entire sample set, right? Anyway, so this shows how far you off are from the average, and then it squares it because whether you missed the bullseye by throwing above the bullseye or below it, you missed, and really we just care, if you missed it by a foot, then it doesn't matter if it was above or below, you're still not very good at darts, right? A foot is pretty significant. You missed the board entirely, essentially, at that point. So the square is just to get rid of the sign there, so that as we add this error up, we're always adding up positive values. And so we square it so that we get something positive, and then we multiply by the probability of that particular sample. So that gives us variance. But we've done a bunch of squaring here, and it kind of feels like we need to correct it on some level. And so that's what standard deviation does. It goes back and it says, well, you kind of blew things up there. I feel like if we need to get something a little more accurate, then we need to take the square root. And so standard deviation is the square root of the variance. And beyond that, standard deviation actually has a further meaning, a further interpretation. So if you have a normal distribution or a bell curve, then 95% of the result set will fall within 2 standard deviations of the average. So you take your mean, or your expected value, the most likely occurrence, and then 95% of all results will fall within 2 times this value, right? The square root of this. Okay. Yeah. Okay, more on stats. I don't really want to focus too much on it this first time around. Okay, and so that moves us to advanced counting techniques. So we'll go through linear homogeneous recurrence relations real quick. We'll do an example, and then we'll call it a day. Okay, so there's a section 8.1. I didn't want to cover it during this first test. I want to come back and discuss it before the second exam. But dynamic programming is just a recursive way to break down other problems, right? So we've kind of discussed it in terms of merge sort, so we've seen the way that recursive algorithms can work. But dynamic programming is a different approach to that. And again, we'll go into this more detail the second time around, chapter 8. Okay, so linear homogeneous recurrence relation of degree k with constant coefficients. It's a mouthful, but essentially it's something of this form, right? And so if it only goes this far, right, it's still linear, a linear recurrence relation with degree k with constant coefficients. So let's break this down, right? So linear, it means that we don't have some previous term squared, right? And or the previous terms are not multiplied by each other. So we're not multiplying an minus 1 times an minus 2 or anything like that. So it's simple in that regard. So it's linear. The homogeneous is that we're not mixing functions here. We don't have some other series b sub n or anything like that we're mixing in here. And we don't have any other function that we're mixing in there. Degree k is just how far back we're reaching in the series in order to compute the next term. So it's a sub n minus k is as far back as we reach. And then the constant coefficients. So the coefficients aren't varying with each iteration. So it's a mouthful. We're saying a lot. I feel like we've taken liberties in mathematics to simplify names of other concepts, right? So I don't understand why it had to be so verbose. But all of this is basically saying that it's of this form. The coefficients are fixed; they're constant, and then we're reaching back k terms. So that's what that mouthful is. So here's an example. Again, the Fibonacci sequence, right? So it's linear, homogeneous of degree 2, and then a sub n is equal to a sub n minus 5. This is actually of degree 5, right? Even though there's only one term over here with a non-zero coefficient, we are reaching back 5 terms, and so it is degree 5 for that reason. Okay, so what does this mean? Like degree k and so forth, what are we talking about here? Well, it turns out that degree just is in polynomials, and because we're about to relate it to polynomials, that is why we're looking for this maximal rank, right? This maximal term that we're reaching back. And so polynomials, like they're several hundred years ago, they were trying to relate it to everything that they could, right? And there was this thought at a time that everything could be described by polynomials, and in some sense that turned out to be fairly accurate. So continuous functions, or functions which have a continuous derivative, can in fact be represented by a polynomial series. And so if you look up the Taylor series for the exponential function, then you get an example of that. But even more than that, there are correction terms. So if you think about ballistics problems where you have this projectile that goes up and it comes down, and you can compute its initial trajectory, and then there's some force like gravity that's pushing it back down and so forth. Then you can approximate its position in time using its x velocity and its y velocity, and then it's the acceleration in the x direction, which is 0 in the frictionless case, right, where there's no wind resistance, right, and then the acceleration in the y direction, which is equal to gravity, and so forth. And so you're taking these first, and you have some initial position, and then you take the first derivative and the second derivative of position with respect to time to get velocity, and then you can correct the velocity over time with the acceleration by taking the second derivative. And if there's more happening, like if it's happening in this continuous way, then you can continue to take these derivatives, essentially infinitely if it's some harmonic motion, and then you can apply these corrective terms, and because it's an infinite series, you can't actually perform an infinite number of additions, otherwise you would never get any results. So you define some amount of error that you're willing to tolerate, and then whenever the error is smaller than that, and you can't actually bound it, if you have the function itself, you can say, well, I just don't want to deal with any error greater than that. So then you wait until the terms shrink small enough, and each higher order derivative plays a smaller and smaller part, right? Just like in the Taylor series. The terms start falling off with factorial speed, basically. And so you can do it. You can use the derivatives to create this infinite series where you start from some initial position, and then over time you can make these predictions and correct them with these derivatives and so forth, and it'll get you there. And so that's one of the reasons that calculus is fantastic, right? That concept works, and beyond just the two-dimensional case with x and y, like it works pretty well, for many variables, for several variables, and so with that result, there was this thought that, oh my gosh, polynomials are the thing. They can do anything, right? And so they tried it. They thought, okay, well, there's got to be some way to make it happen, and just with persistence and dint of will, they were able to find this relationship where recurrence relationships could also be described in terms of polynomial. And so when you look at this, if you're like me, you look at this and you say, okay, well, but why? Why did they make this substitution of an for rn? And essentially it's because, well, they need to compute the next term. And for any polynomial, if you can put it in monic form, so you have the r to the n plus the smaller terms and so forth. And if there's something that you're multiplying r to the n by, right, and you have all that other junk, and then it equals 0 at the end, well, just divide whatever you're multiplying that by, and you can get a polynomial with the same roots. It's not strictly the same function, right? But it has all of the same zeros, all of the same roots. And so it's not so unrealistic to think that you could get a function that would satisfy this. And so they said, okay, well, we'll just assume that exists, right? And so it takes a little bit of a leap of faith, and it's kind of confusing. And you think, well, when was I supposed to have learned the stuff that it took for me to derive this myself? I'm like, well, it took a while for them to come up with this on their own, right? And so it's pretty, advanced mathematicians in their time, and they came up with it. But it was just this belief that polynomials would eventually be able to describe everything. That's for continuous functions that are differentiable. Polynomials can pretty much do it, but they start running into troubles if you introduce any poles and stuff like that. But okay, so then we say, okay, well, we can equate a sub n to some polynomial r to the n, and if it's true for r to the n, then it was probably true that a sub n minus 1 was equal to r sub n minus 1, and then a sub n minus 2 was equal to r sub n minus 2, right? All we're doing is replacing the n here. So, well, if these two are equal, then each of these or previous terms would have been equal, and if those were equal, then we wouldn't necessarily need to change the constants at all. So then this would take this form, right? And then, well, okay, well, now we have a polynomial, and we want to get it equal to 0 so that we can start computing roots and stuff like that. We have it in some familiar form, so now we have it like that. But this is just going to grow each time we increase our term in. What if we simplify this a bit and we divide both sides by r to the n minus k? Then we get this version whose roots we don't have to compute to arbitrarily high numbers, high degrees of n. And so that division by r to the n minus k is valid if r is not equal to 0, because dividing by 0 generally blows up math. Like, it's not considered a good thing. Multiplying by infinity and dividing by 0, you should definitely take those out of your repertoire. Okay, so then we have, so if we make that simplification, then we don't have n scaling off to infinity, and we have some polynomial with constant, that has some sense of constancy, right? So k is the degree of the recurrence relation. The constants came from over here in the original definition. Now we have it equal to 0, so we can just compute this, right? Like r, we should be able to compute that given that we have these constants. And so this is called the characteristic polynomial of the recurrence relation. We made some leaps of faith. We declared polynomials to be the end-all be-all, which they're pretty nice. Polynomials are nice, but there's more to life than polynomials. And then we simplified because we didn't want to have to compute and we weren't even sure if it would yield anything, but we didn't want to have to compute the roots each time we increased our term a sub n. Right? So we wanted something that described the entire sequence. So in order to do that, we got rid of n by dividing both sides, the right hand and the left hand side, right? Left hand and right hand, by r to the n minus k. Okay? And so then we got the characteristic polynomial. So it's the leap of faith in a couple hops we got there. Okay, so we have this. What do we do with it? Well, the first thing we need to do is compute the characteristic roots. Well, why do we want the characteristic roots? We're still not even sure if this describes anything. Well, neither were the people that came up with this, but they just kept pushing and pushing, and by blind faith they believed that they would eventually be able to find some link between recurrence relations and polynomials. And it turned out that in a very specific case, when it is linear homogeneous recurrence relation of degree k with constant coefficients, by George, there is a link. Right? But so it's fascinating that they found it at all, but I understand, when you're learning it, it seems a little convoluted and not exactly sure why they're doing any of it. But they did it, and it worked, and it turns out to be the solution for this very specific case. Right? So, okay. So in that case, we have our characteristic roots. And so let's consider the case where it's degree 2. Then we have, so then we would have something of this form, right? Which, and this is the theorem. So it becomes a function of this form. And so both roots are raised to the n, right? And that's how we continue to get our new values. But we compute the roots, right? We compute r1 and r2, and because it's squared, we could use the quadratic equation to solve the roots given c1 and c2, which are constants of the relation. So we can just find it, right, where it's degree 2. That's not so bad. And so then the final form, the closed form solution, would be of this form. So again, we return to Fibonacci because it's something that's very familiar to us. And we have our initial conditions, and then we're able to solve the characteristic roots just using the quadratic equation, and we get these values. And so the theorem tells us that there's some constants. So alpha 1 and alpha 2 are not the same constants that we started with. So we have to actually solve for those. Well, the quadratic equation spotted us the roots, so we already have that. And we know that f of n is of this form. So all we need to do is pick n equal to 0 and n equal to 1, and then take the solutions from those and use that to create a system of equations so that we can solve for alpha 1 and alpha 2. So we know the final solution will be of this form, but we need to find alpha 1 and alpha 2. So let's take what we were given, the initial conditions, right? And then plug it in. And so it's of this form, right, r to the n, but n is equal to 0, so the roots just vanish. We get alpha 1 plus alpha 2 equals 0. So I know that alpha 1 and alpha 2 have the opposite sign, right? Like you just plop this over here and you get alpha 1 equals negative alpha 2. So we could make that substitution here, right? But let's set up the other one. So again, we know that it's of this form, alpha 1 times r1 to the n plus alpha 2 times r2 to the n. But n is equal to 1, so, and we already know these values, so we don't have to square it or cube it or do anything weird to that. We just make the substitution, and we have alpha 1 and alpha 2, okay? And then we could again use the fact that alpha 1 is equal to minus alpha 2, plug in a substitution. And we already know that f1 is equal to 1 because that was one of the initial conditions, okay? So then if you solve it from there, right, you make the substitution, you solve for either alpha 1 or alpha 2, and then use the fact that it's just a sign flip. then you get that alpha 1 equals 1 over square root of 5, and alpha 2 equals negative 1 over, negative 1 over the square root of 5. Okay, so now we have those, so we plug it back into our formula, right? Now, instead of alpha 1 and alpha 2, we have 1 over square root of 5 and minus 1 over square root of 5. And so this is the closed form solution. And you may be asking yourself, well, what are we doing with the square root of 5 in there? Like, we're only dealing with, beyond just rational numbers, we're dealing with whole numbers. The Fibonacci sequence is entirely integers, right? So there's something we could do to get rid of that. And we'll come back to that question at a later date. But that's the closed form solution. So, okay. Yeah. Okay. Yeah, let's call it. That's fine. So we'll pick up here next time. We're not going to be solving any non-homogeneous problems, but these next two theorems deal with just the general case. So we dealt with the degree 2 case, right? And so this one deals with the case of multiplicity, right? So that's fine. We'll go over the next three theorems and then we'll be done for the day. So what happens if R1 equals R2? So here they differed by this sign, right? So it was 1 plus square root of 5 and 1 minus square root of 5. But what would have happened if they were both 1 plus square root of 5? How would we have plugged that into the equation? Like it seems like it would have altered it some. And in that case, for each time there's a multiplicity, so you solve here, let me correct myself. So instead of it being R1, alpha 1 R1 to the n plus alpha 2 R2 to the n, because they're the same root and they just occurred the same, then they would end up just being collapsed into a single variable, and you would just correct the coefficient. But that turns out to not be an accurate way to compute it. And so it turns out that the correct fix for that scenario is to multiply by n. So if in a degree 2 case, the quadratic case, it's not possible to have a multiplicity higher than 2. But let's say that it was cubic, and it was the same root with a multiplicity of 3. Then the solution would be of the form an times alpha 1 times the root to the n plus alpha 2 times n times the root to the n plus alpha 3 times n squared times the root to the n. And so for however many times that n or that root is repeated, you multiply by n, right? So if it's not repeated, then it stays simple, right? If it's repeated once, right? So if the multiplicity is 2, then it's repeated once. Then you multiply by n. If it's repeated twice, or the multiplicity is 3, then you would multiply by n squared. But you have to keep all of those other versions, right? Because that root happened, right? It's just happening again and again. And so in order to correct for that, you have to add this in here. So, well, okay, this theorem doesn't say that. Shouldn't it be put in some general form? I'm glad you asked. So if the polynomial, the characteristic polynomial is degree k, and you have that multiplicity of roots again, right? So here you have the sequence of the form. This is the recurrence relation. Then the solution will take on this form. Okay, so we've only done it for degree 2 so far. So this is the simple case, right? So they're all distinct roots. Then it follows nicely. This looks exactly like what we did for degree 2. But what happens if we have multiplicities? Well, okay. So keep in mind that if the multiplicity is 1, right? Like if it doesn't repeat at all and it's a unique root, so of the k possible roots, then all of this, it just simplifies, and it's just some constant alpha, which you have to use a system of equations to solve for, times that root to the n. Okay, but what the rest of this junk is saying is that, well, just what I was saying, if it's repeated, then whatever the multiplicity is, minus 1. So if it's repeated, if the multiplicity is 3, then it's repeated 2 times. So then this would be 3 minus 1. So you would end up with an n squared here. Okay? But it's a constant times the root, and then if it's repeated, then that root, it gets repeated, but each time you tack on n, and then n squared, and then n cubed, and so forth in that pattern. Right? And so why are we repeating all of this junk? It's like, well, because it's possible. So if you have a degree 10 polynomial, and you have 5 distinct roots, each one repeated twice, then or each one with a multiplicity of 2, then you would have 5 roots, so R1, R2, and so forth up to R5, each with their own constant coefficient, and then each with a twin pairing term, if you want to call it that, or I don't know exactly what the proper name would be, but each with a paired term where you multiply by n, right? So that's the correction for multiplicity. I don't know how to describe it beyond that. Okay, and then next time we'll pick up with linear non-homogeneous recurrence relations with constant coefficient. So this is the non-homogeneous, so it's not all the same, non-homogeneous, right? Okay. All right, remember to check for that homework today, and that'll be due next time. And the first exam will actually be 2 weeks from today. So I will provide you with a review next Tuesday. All right, have a great day.